When you think about what lies at the very center of black holes, what comes to your mind? For years, most scientists said that there was a point there called a singularity, where density becomes infinite. But what if this is merely an illusion, a deception played on us by mathematics? What if the universe actually has hidden safety systems that prevent such extreme conditions from ever taking place? Today, we will examine this question in depth and dive into the wildest theories of modern physics. Let's begin. The moment mathematics breaks down. What happens when you try to divide by zero on a calculator? It gives an error, right? This is exactly what happens when physicists try to calculate the center of a black hole using Einstein's equations. The mathematics doesn't just become difficult or complicated, it completely stops working. The equations begin to spew infinities like a broken machine, and this is the problem that has troubled physicists for nearly a century. When matter begins to collapse under its own gravity, Einstein's theory of general relativity predicts that this collapse continues without limit. Density keeps increasing. First, atoms are pushed closer together. Then, electrons crash into protons. Eventually, even neutrons can no longer withstand the pressure. But the crushing doesn't stop there. According to mathematics, matter continues collapsing until it reaches infinite density at a single point, a point with zero volume. Physicists call this nightmare scenario a singularity. Imagine trying to compress the entire population of New York City into a space smaller than the period at the end of a sentence, and then continuing to compress it. The curvature of space-time around this point also becomes infinite. Picture rolling a bowling ball onto a trampoline, creating a dip in the fabric. Now imagine that dip becoming so steep that it turns into a bottomless pit and tears the trampoline apart completely. That is what a singularity does to the fabric of reality. At this point, time loses all meaning. Distance no longer matters. Every law of physics we have ever discovered gives up and returns mathematical nonsense. It's as if nature itself throws up its hands and says, "I can no longer calculate this." And here is the truly disturbing part. Our most trusted theories predict that these mathematical monsters must exist at the center of every black hole in the universe. That means millions of points where physics completely breaks down are scattered throughout space right now. Some black holes contain the crushed remains of stars more than 20 times the mass of our sun, all compressed into mathematical points smaller than a grain of sand. Even worse, cosmologists believe that our entire universe emerged from a singularity during the Big Bang. According to this view, everything we see around us, from planets to galaxies, down to the atoms in your body, somehow expanded from a point of infinite density and temperature. Mathematics tells us that at the very beginning of time, physics was not just broken, it was completely meaningless. This creates what philosophers call a crisis of explanation. How can our most successful scientific theories predict their own destruction? How can the mathematics that accurately describes everything from GPS satellites to gravitational waves suddenly produce answers that have no physical meaning at all? The outcome Einstein never wanted. Einstein never wanted his theory to destroy physics itself. When he developed general relativity in 1915, his equations were meant to describe how massive objects bend the fabric of spacetime. Stars, planets, even beams of light would follow curved paths through this distorted cosmic geometry. It was an elegant mathematics that transformed gravity from a mysterious force into the natural motion of objects through curved space. But mathematics has a habit of revealing truths even its creators never anticipated. Within just a few years, Other physicists began discovering solutions hidden inside Einstein's equations that deeply disturbed him. These solutions described scenarios where matter could collapse so completely that it vanished from the universe entirely, leaving behind regions where space-time itself became infinitely curved. Einstein fought against these conclusions. He published papers attempting to prove that such extreme collapses could never occur in nature. He argued that quantum effects, the rotation of stars, or some other physical mechanism would always prevent total gravitational collapse. He believed the universe must contain natural limits that stop matter from crushing itself into nothingness. The problem was that Einstein's own equations did not agree with him. Within general relativity, there is no stopping mechanism. When enough matter is packed into a sufficiently small region, the mathematics demands that collapse continues without end. This is what troubles physicists so deeply. General relativity has passed every experimental test we have ever thrown at it. The theory correctly predicted that massive objects would bend starlight, that time would flow more slowly in strong gravitational fields, and that accelerating masses would generate ripples in spacetime. When scientists detected gravitational waves from colliding black holes in 2015, the signals matched Einstein's predictions with astonishing precision. So we possess a theory that works perfectly for everything from falling apples to orbiting planets to colliding galaxies. And yet, that very same theory predicts that under extreme conditions, physics itself completely breaks down. It is like owning a car that runs flawlessly on every road except the ones where you need it the most. The saving role of quantum physics. At the smallest scales of reality, matter refuses to stay fixed. Quantum mechanics tells us that particles have no definite positions or velocities until they are measured. They exist as probability clouds spread through space, like ghostly possibilities waiting to become real. An electron orbiting an atom does not follow a precise path like a planet orbiting the sun. Instead, it exists as a fuzzy probability cloud, occupying many positions at once. This quantum fuzziness may be exactly what saves the universe from singularities. As matter is compressed to extreme densities, quantum effects become increasingly dominant. The familiar rules of classical physics begin to collapse, replaced by the strange logic of quantum mechanics, a world where particles can tunnel through barriers and exist in multiple states simultaneously. Imagine trying to squeeze a handful of ping-pong balls into a box that keeps getting smaller. At first, you can pack them closer together by reducing the empty space between them, but eventually you reach a limit where the balls themselves begin to resist further compression. As you try to make the box smaller, they push back against the walls with increasing force. Quantum particles behave in a similar way, but with a crucial twist. As they are confined to smaller and smaller volumes, quantum uncertainties actually increase their effective size. The more precisely you try to confine a particle's position, the more violent its quantum motion becomes. This gives rise to what physicists call quantum pressure, or degeneracy pressure. When matter reaches densities of around 10 to the power of 15 grams per cubic centimeter, quantum effects generate an enormous outward pressure capable of halting gravitational collapse. This is roughly equivalent to compressing all the cars on Earth into a volume the size of a sugar cube. At such extreme densities, quantum mechanics is essentially rebelling against further compression. But for the most massive stars, even this quantum resistance may not be strong enough to stop collapse entirely. The Planck scale and the structure of space. Space itself may be made of unimaginably tiny building blocks. For more than a century, physicists assumed that space-time was smooth and continuous, like a perfectly flat sheet of paper that could bend and stretch without limit. Einstein's general relativity treats space as an infinitely divisible fabric, one where you can always zoom in further and find ever smaller regions. No matter how closely you examine it, the geometry remains smooth. But what if this assumption is completely wrong? What if, at the smallest scales, space turns out to be granular and discrete, like a digital photograph when you zoom in far enough? This radical idea forms the foundation of one of the leading attempts to unite Einstein's relativity with quantum mechanics, loop quantum gravity. According to this theory, space is built from fundamental units known as loops, existing at the Planck scale. These loops are unimaginably small, roughly 10 to the power of -35 meters across. To put that into perspective, a single Planck-length loop is smaller compared to a proton than a proton is compared to the entire solar system. Imagine zooming in on an image on your computer screen. From a distance, the picture looks perfectly smooth and continuous. But as you zoom in further and further, individual pixels begin to appear. Zoom in even more, and smooth curves and gradual color transitions dissolve into a grid of discrete squares, each with its own fixed color value. Quantum loop gravity suggests that space works in a similar way. The smooth geometry we observe at large scales emerges from the collective behavior of countless quantum loops at the smallest scales. Just as digital images are built from pixels, the fabric of reality itself may be constructed from these fundamental atoms of space. This pixel-like structure of space creates a natural stopping point for gravitational collapse. Matter can only be compressed down to the size of a single spatial pixel. Try to compress it further, and you are effectively demanding that matter occupy less than 1 unit of space itself, something that is mathematically impossible. When collapsing matter reaches this fundamental limit, something extraordinary happens. Instead of forming a singularity, the matter rebounds with immense force. The quantum geometry of space itself provides the resistance, like a trampoline that can stretch only so far before snapping back. String theory and the vibrating universe. What if every particle in the universe is actually a vibrating string? This isn't poetic language or philosophical speculation. It is one of the most ambitious attempts to describe reality at its deepest level. String theory proposes that all fundamental particles are not points, but tiny one-dimensional strings vibrating in multiple dimensions. An electron is not a point particle, but a string vibrating in a specific pattern. A photon is the same string vibrating in a different way. These strings are unimaginably small, operating at the Planck scale, where our ordinary notions of size and distance begin to break down. Yet, despite their tiny size, they may hold the key to preventing singularities from ever forming anywhere in the universe. The critical insight comes from how strings behave under extreme compression. Unlike point particles, which can theoretically be squeezed into infinitely small regions, strings possess a natural minimum size. You can compress a vibrating guitar string only to a certain point. You cannot make it smaller than the wavelength of its fundamental vibration. Push beyond that limit, and the string snaps back with tremendous force. Cosmic strings in string theory behave in a similar way, but with a quantum twist. As matter collapses toward what would normally become a singularity, the fundamental strings composing that matter begin to vibrate more and more violently. This growing vibrational energy produces what physicists call stringy effects, generating enormous outward pressure. You can compress a vibrating guitar string only to a certain point. You cannot make it smaller than the wavelength of its fundamental vibration. Push beyond that limit, and the string snaps back with tremendous force. Cosmic strings in string theory behave in a similar way, but with a quantum twist. As matter collapses toward what would normally become a singularity, the fundamental strings composing that matter begin to vibrate more and more violently. This growing vibrational energy produces what physicists call stringy effects, generating enormous outward pressure. Imagine blowing air into a balloon. At first, the balloon expands smoothly as you add more air, but there comes a critical point where the rubber can stretch no further. Add just a bit more air, and the balloon explodes with surprising violence. String theory suggests that collapsing matter behaves the same way, like an overinflated balloon. Instead of collapsing inward forever, stringy effects cause matter to burst outward once a critical density is reached. The information paradox and the holographic principle. It turns out that information in our universe cannot be destroyed. This isn't about computer files or library books. In physics, information means the complete quantum description of any system, a single particle, a complex molecule, or an entire star. Quantum mechanics tells us that this information can never be created or destroyed, only transformed from one form into another. It is as fundamental as the conservation of energy itself. But black holes seem to violate this sacred principle. When matter falls beyond the event horizon, all the quantum information it carries appears to be lost forever inside the singularity. From the perspective of the outside universe, that information is permanently erased from reality. This creates one of the deepest puzzles in modern physics, the information paradox. The paradox becomes even more troubling when Hawking radiation is taken into account. Stephen Hawking showed that black holes slowly evaporate by emitting random thermal radiation over enormous timescales. Even the largest black holes will eventually disappear completely, leaving behind only this seemingly random energy. If the original information that fell into the black hole is not somehow encoded in that radiation, then it has been destroyed forever. But recent breakthroughs suggest that the information paradox may actually be evidence that singularities do not exist. If information truly cannot be destroyed, then black holes must have a mechanism for preserving all incoming quantum data and eventually returning it. That would be impossible if the information were crushed into a region where physics completely breaks down. The holographic principle offers a radical solution. It proposes that all the information associated with a black hole is encoded in quantum fluctuations on the two-dimensional surface of its event horizon. Think of a hologram on a credit card. When you tilt it in the light, it appears three-dimensional. Yet all the information that creates that illusion is stored on a flat, two-dimensional surface. The holographic principle suggests that black holes may work the same way. What appears to be a three-dimensional interior filled with falling matter could actually be a projection created by information patterns on the black hole's surface. The firewall hypothesis. In 2012, a group of physicists led by Ahmed Amhiri dropped a bombshell that has divided the physics community ever since. They argued that the event horizon may not be the smooth, invisible boundary we always imagined. Instead, it may be surrounded by a wall of extraordinarily high-energy radiation, one that would instantly vaporize anything attempting to cross it. This firewall hypothesis emerged from attempts to resolve the information paradox we discussed earlier. If black holes must preserve all the quantum information that falls into them, then the Hawking radiation that escapes must be quantum entangled with the matter inside the black hole. But quantum mechanics forbids a single particle from being fully entangled with two different systems at the same time. The mathematics forces a brutal choice. Either Hawking radiation remains entangled with the black hole's interior, preserving information, but creating a firewall at the horizon, Or the radiation is not entangled, allowing smooth passage across the horizon, but destroying information forever. If the firewall exists, it would be unlike anything else in the universe. The energy density at the event horizon could approach the Planck scale, generating temperatures so extreme that all matter would be instantly converted into pure energy. Falling into a black hole would not be a gentle journey toward a crushing singularity. It would be instantaneous annihilation in a furnace of quantum fire. The gravastar model. What if black holes aren't actually holes at all? What if they are dark energy bubbles disguised as collapsed stars? This isn't just wild speculation. It is a serious theoretical proposal known as the gravastar, short for gravitational vacuum star. According to this idea, objects we call black holes are actually hollow spheres filled with repulsive dark energy surrounded by an ultra-thin but ultra-dense shell of normal matter. Imagine blowing a soap bubble, but instead of air inside, the bubble contains a form of energy that pushes outward with enormous force. The soap film represents a shell of matter compressed to nearly infinite density, while the dark energy interior pushes back with precisely the right strength to prevent collapse or explosion. The result is a perfectly stable object that looks indistinguishable from a black hole from the outside. The gravastar model emerges from our growing understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy has a strange property. Instead of creating attractive gravity, it produces repulsive gravity. While normal matter pulls things together, dark energy pushes them apart. Most of the universe is made of this strange anti-gravitational substance, and yet we barely understand what it is or how it works. But what if dark energy plays a crucial role in preventing singularities? When matter collapses under extreme gravitational pressure, it may trigger a phase transition that converts normal matter into dark energy. Instead of being crushed into infinite density, the collapsing material transforms into its opposite, becoming a source of outward push rather than inward pull. Emergent gravity. Gravity may not be a fundamental force at all. It may be an illusion emerging from deeper quantum processes, an idea that challenges everything we think we know about the force that shapes the cosmos. For more than 3 centuries, we have treated gravity as one of nature's fundamental forces, as basic as electromagnetism or the nuclear forces that bind atoms together. But what if gravity is more like temperature or pressure? Not fundamental properties, but emergent ones, arising from the collective behavior of countless microscopic components. Consider the temperature of a gas. Individual molecules do not have temperature, they simply move with different speeds and directions. But when trillions of molecules bounce and collide together, their collective motion creates what we experience as heat. Temperature is not a fundamental property of matter. It is an emergent phenomenon arising from underlying molecular chaos. Emergent gravity theories suggest that space-time itself may work the same way. At the deepest level, reality may be composed of quantum bits of information that experience no gravity at all. But when vast numbers of these information units interact together, they create the illusion of curved spacetime and gravitational attraction. What we call gravity would then be a collective effect, like the temperature of a quantum gas. Future experiments and discoveries. To test whether singularities truly form, scientists are attempting something extraordinary. They are creating artificial black holes inside particle accelerators. These are not the massive stellar giants drifting through space. Laboratory black holes would be microscopic, fleeting entities that exist for only the briefest moments before completely evaporating. Yet, despite their tiny size and temporary existence, they may hold the key to understanding whether nature truly allows real singularities to exist. These experiments collide particles at energies approaching the Planck scale, where quantum effects begin to dominate over gravity itself. When protons collide at such extreme energies, they recreate conditions of matter and energy density not seen since the earliest moments after the Big Bang. If singularities can form under any circumstances, these experiments should be capable of creating them. Think of it like stress testing a bridge. Engineers gradually add more and more weight, not to destroy the bridge, but to discover exactly where and how it fails. Physicists are doing the same to space-time itself. They are pushing matter and energy to ever more extreme densities to see whether reality has a breaking point. At CERN, the Large Hadron Collider has produced the highest energy densities ever achieved under controlled conditions. When lead nuclei collide at near light speed, they generate temperatures more than 100,000 times hotter than the core of the Sun, and pressures capable of compressing matter to densities rivaling neutron stars. Yet despite these extreme conditions, no singularities have ever been observed. Instead, the experiments revealed something remarkable. At extreme densities, matter appears to undergo phase transitions that prevent infinite collapse. Quarks and gluons, the fundamental building blocks of protons and neutrons, separate into a new state of matter known as quark-gluon plasma. This plasma behaves like an almost perfect liquid, with properties that seem designed to resist further compression. Even more intriguingly, as the plasma expands and cools, it does not collapse back toward infinite density. Instead, it freezes into normal particles through a process that appears to include built-in safeguards against runaway collapse. It is as if nature itself possesses multiple redundant systems designed to prevent matter from ever reaching the densities required to form singularities. The absolute compression limit of matter. Every form of matter in the universe may have an ultimate, unbreakable limit to how much it can be compressed. We already know this to be true for certain types of stars. The Chandrasekhar limit tells us that white dwarf stars cannot contain more than about 1.4 times the mass of our Sun. Beyond this threshold, the quantum pressure that supports the white dwarf against gravity is no longer strong enough. The star must either explode as a supernova or collapse into something even denser. Neutron stars follow a similar rule. They have their own final mass limit, known as the Tolman-Oppenheimer-Volkoff limit. Pack more than about 3 solar masses into a neutron star, and even the incredibly strong nuclear forces holding neutrons together can no longer resist gravity. But what if this pattern continues all the way down? What if there exists a final limit for all matter, a point beyond which no physical force or quantum effect can prevent collapse? Paradoxically, this absolute limit may be exactly what prevents singularities from forming. Imagine a trapeze artist performing high above the ground. Below them is a series of safety nets, each one stronger than the last. The first net is sufficient under normal conditions, but if it fails, a stronger net waits beneath it. And if that one fails, an even stronger net lies below. Each successive safety net is designed to withstand more extreme conditions than the previous one. Matter may behave in exactly the same way. When gravitational pressure overwhelms the quantum forces that support normal atoms, those atoms collapse into neutron stars. When gravity overwhelms the nuclear forces that support neutrons, matter may collapse further into even more exotic forms, quark matter or strange matter. Each transition represents a new form of quantum resistance that activates at higher densities. But the final safety net may not be matter at all. It may be space and time themselves. At the Planck density, roughly 10 to the power of 94 grams per cubic centimeter, the very concepts of space and time begin to break down. This is not merely another phase transition. It represents a fundamental boundary where the mathematical tools we use to describe compression simply stop making sense. Imagine trying to compress matter into a region smaller than space itself allows. It would be like forcing a basketball into a container the size of a marble. The basketball does not become infinitely dense. It simply cannot fit. In the same way, matter may not be compressible beyond the fundamental granularity of spacetime itself. Wormholes and spacetime tunnels. What if the center of every black hole is not an end, but a gateway? Not a science fiction fantasy, but a serious possibility that emerges naturally from Einstein's equations when followed to their logical conclusions, without assuming that singularities must form. If matter cannot collapse into infinite density, then the space-time geometry inside black holes may fold in on itself, creating tunnels that connect distant regions of the universe. Imagine space-time as a vast, tightly stretched rubber sheet. Normally, massive objects create dimples in this sheet, and smaller objects roll along the curved paths formed by gravity. But what if the most massive objects create depressions so deep that they punch completely through the sheet, forming holes that connect to other regions of the cosmic fabric? These space-time tunnels are known as Einstein-Rosen bridges, or more commonly, wormholes. The mathematics describing them has existed since the 1930s, but for decades, physicists assumed that wormholes could not exist in the real universe because they appeared to require exotic matter with negative energy density to remain stable. However, if singularities are impossible, black holes may naturally evolve into wormhole-like structures without any exotic matter at all. Here's how it could work. As matter falls inward to what would traditionally become a singularity, quantum effects grow stronger. Eventually, these effects generate an outward pressure that overwhelms gravity's inward pull, preventing infinite compression. But instead of simply bouncing back, this quantum rebound may be so violent that it tears the fabric of spacetime itself. The tear does not destroy spacetime. Instead, it connects it, linking one region to another, possibly in a distant part of our universe, or even in an entirely separate cosmic domain. Matter falling into a black hole would not be crushed out of existence. Instead, it would pass through this space-time tunnel and re-emerge somewhere else, transformed but preserved. Black holes may not be cosmic graves. They may be bridges. The universe correcting itself. What if the universe is fundamentally self-correcting, automatically preventing any scenario that would lead to logical contradictions? This idea, known as the bootstrap paradox or the principle of consistency, suggests that the laws of physics are structured to prevent their own violation. Much like a well-designed computer program with robust error-handling routines, which automatically correct or reject commands that would crash the system, the universe may contain built-in safeguards that prevent situations capable of breaking reality's core rules. Think of it as a cosmic immune system. When your body encounters a virus or harmful bacterium, specialized cells automatically activate to neutralize the threat before serious damage can occur. In a similar way, when conditions arise that could lead to singularities or other mathematical breakdowns, the universe may automatically deploy quantum effects, limits on space-time curvature, or other mechanisms to neutralize the threat to physical law. This is not mystical thinking or anthropomorphic projection. It is a serious hypothesis about how quantum mechanics and general relativity may work together at the deepest level of reality. The idea is not that the universe possesses intelligence in the sense of conscious thought, but that it contains self-regulating structures designed to preserve consistency and prevent paradox. Reality may not simply obey laws, it may actively protect them. Quantum foam. At the smallest scales of reality, space and time themselves may be constantly boiling with virtual particles and spontaneous fluctuations. Imagine zooming in on the surface of the ocean with an increasingly powerful microscope. From a distance, the water appears perfectly smooth and calm. But as you look closer, you begin to see ripples, then waves, then individual water molecules bouncing in chaotic thermal motion. At the molecular level, what once looked like a stable surface reveals itself as a seething mass of constant activity. Physicists believe space-time itself may work the same way. At the scale of everyday experience, space appears as a smooth, continuous fabric that can be gently curved by massive objects. But zoom in toward the Planck scale, around 10 to the minus 35 meters, and this smooth geometry may dissolve into a froth of quantum fluctuations, where the very concepts of distance and duration lose their meaning. This quantum foam is made of virtual particles that borrow energy from the vacuum and repay the debt so quickly that the universe's accounting system never notices. Space itself may be built from these fleeting quantum events, flickering billions of times per second, like the frames of a film screen, creating the illusion of smooth motion. At these scales, the normal rules of physics completely break down. Particles can tunnel through barriers that should be impassable. Energy can be borrowed from nothingness and returned again. Cause and effect blur as quantum events unfold faster than information can travel between them. This is a realm where logic itself becomes probabilistic, not absolute. And this quantum foam may be exactly what prevents singularities from forming inside black holes. As matter is compressed toward Planck-scale densities, it encounters a boiling quantum chaos where the smooth space-time description that predicts singularities simply stops making sense. You cannot compress matter into a region smaller than the quantum foam bubbles that make up space itself. The observation and measurement problem. Observing a singularity may be fundamentally impossible under the laws of quantum mechanics. This is not merely a practical limitation of our current technology. It may be a deep physical principle that makes singularities literally unobservable, even in principle. And if something cannot be observed under any circumstances, quantum mechanics suggests that it may not exist in any meaningful physical sense. The problem begins with the fundamental rules of quantum measurement. In quantum mechanics, the act of observation changes the system being observed. This is not because our measuring devices are clumsy or intrusive. It is a fundamental feature of reality at the quantum scale. Until a measurement is made, the universe exists in a quantum superposition, selecting a single outcome from all possibilities only at the moment of observation. But what happens when you attempt to observe something that would require infinite measurement precision? A true singularity would possess infinite density, infinite curvature, and occupy zero volume. Measuring any one of these properties with perfect accuracy would require infinite precision, infinite energy, and measurement tools with zero size. quantum mechanics tells us that such measurements are not just practically impossible, they are theoretically meaningless. What the coming years may reveal. Over the next few decades, we may develop instruments precise enough to directly test whether singularities truly exist inside black holes. This technological revolution will not come from building larger telescopes or more powerful particle accelerators. Instead, it will emerge from our growing ability to detect and manipulate individual quantum particles with near-perfect precision. These quantum sensors may become sensitive enough to probe the informational content of Hawking radiation and determine whether it carries signatures of singularity formation. The key insight is this: if singularities do not exist, then the Hawking radiation emitted by black holes must contain subtle patterns reflecting the exotic quantum processes occurring within. Every photon in that radiation would carry a tiny fragment of information about the black hole's internal structure. Advanced quantum detectors could read this information like a cosmic message encoded in starlight. Space-based gravitational wave observatories may provide another powerful way to test singularity theories. When black holes merge, they create ripples in spacetime that carry information about their internal composition. If the merging objects contain exotic quantum cores rather than singularities, the gravitational wave signatures should differ subtly yet detectably from the predictions of Einstein's classical theory. Future quantum computers may also play a crucial role, simulating black hole formation with unprecedented accuracy. These machines could model the quantum effects that prevent singularity formation, allowing physicists to make precise predictions about observable signatures that are far beyond the reach of today's computers. Conclusion: on the edge of a new era in physics. If singularities do not exist, then we stand at the threshold of the greatest revolution in physics since the discovery of quantum mechanics. The consequences reach far beyond black holes. From cosmology to particle physics to quantum gravity, every branch of theoretical physics would need to be rethought in light of this fundamental discovery. We would be living through a transformation comparable to the shift from Newton's clockwork universe to Einstein's relativistic cosmos. Consider what this would mean for the Big Bang. If singularities are impossible, then our universe could not have emerged from a point of infinite density. The standard cosmological model would need to be replaced by bouncing universe scenarios, eternal inflation theories, or entirely new frameworks we have not yet imagined. The very idea of a beginning of time might be abandoned in favor of cyclic or eternal models. Particle physics would face equally dramatic changes. The mathematical tools physicists use to calculate particle interactions often rely on integrating over infinities and then removing them through renormalization. If nature truly avoids infinities, then these methods may be pointing towards something profound about the structure of reality itself. Theories that naturally eliminate infinities may reveal more fundamental definitions of matter and energy. This revolution would also transform our understanding of information and computation. If black holes preserve information through exotic quantum processes instead of destroying it in singularities, then the universe itself behaves like a vast quantum computer that never loses data. This could reshape our understanding of consciousness, artificial intelligence, and the relationship between physical processes and information. But perhaps the deepest change would be philosophical. For centuries, physicists accepted that their theories might collapse under extreme conditions. Singularities represented the ultimate breakdown, points where mathematics itself surrendered. If these mathematical monsters do not exist, then the universe may be far more elegant and self-consistent than we ever dared to hope. This could mark the beginning of a beautiful era of physics, where mathematical elegance and physical intuition work in harmony. Instead of accepting ugly infinities and arbitrary parameters, physicists may discover that reality operates according to principles of mathematical beauty and logical consistency that forbid exceptions. The technologies emerging from this revolution could be transformative. Understanding how quantum effects prevent singularities might teach us how to manipulate space-time itself, enabling advances in transportation, communication, and energy production that would appear magical by today's standards. If black holes are not cosmic destroyers, but cosmic recycling centers, we may one day learn to harness their exotic physics for purposes we can barely imagine. The search for a theory of everything would gain new urgency and new hope. Rather than trying to unite theories that fail under extreme conditions, physicists would seek a single mathematical framework that remains beautiful and consistent under all possible conditions. Such a theory might finally explain why the universe exists at all and why it operates according to the particular laws we observe. We stand at the edge of answering one of the deepest questions ever asked. Does mathematics describe reality, or does reality transcend mathematics? The answer may reshape not only physics, but our entire understanding of existence itself. And this journey is only just beginning. If you want to continue this journey together, don't forget to subscribe and leave a like. Good night.